Hello, and welcome to my the ninth in my series of videos, all under the umbrella title of An Absolute Relativity. And in this one, I do hope to bring it more together as to why I've called it An Absolute Relativity. And the last one was about protons and what they are not, and this one is protons and what they are. And a whole lot more than that, but essentially what protons are. Now I hope you've watched all the others, because the whole thing's supposed to be a sequence which makes absolute sense of what I'm saying. When I say that the plethora of particles that have been invented by modern quantum mechanics do not exist. And all the way through I've been showing that is so. And okay, this is protons and what they are, but just a little brief look at this is what the proton, essentially what I was saying in the last video, this is what protons are not. They do not consist of quarks up, quarks down, quarks, charm quarks, whatever other quarks. There are no quarks in there. So what's at the heart of every proton? And as I said before, protons are the building blocks of all the atoms. All the atoms are made of protons. And neutrons are protons, kind of absorb protons with another little bit of energy. So that all there are protons. Protons build everything. I've shown how the electron, the photon do not actually exist. They're effects on the energy levels of each proton. So what is the proton? What's the heart of it? Just bring up this. You can see here, I've always considered this a very clumsy illustration of the way mass distorts space-time, as it's some kind of mesh or rubber mat. The rubber mat thing has been around for a long time, that the ball sits in the rubber mat and goes around there in warped space-time, and a neutron star, and the amount of warping of space-time depends on the mass, and the neutron star being much denser than the atoms of the sun will warp it more, and then the black hole will warp space-time to such an extent that nothing can escape from its the escape velocity from a black hole would have to be faster than the speed of light, and nothing is faster than the speed of light, thereby nothing can escape from a black hole. But apparently now black holes do evaporate. Still, that's all another subject. But light itself cannot escape from a black hole. So, why have I jumped straight into talking about gravity and about black holes? At this point, I just want to quote. I'm going to be reading quite a bit. and I'm going to be referring to a particular paper, and there's a link I've published with this video to that paper. Well worth seeing, but essentially I'm reading from Boyan Gorank, who published an article about this paper and about its author. And he's saying, after some 20 years of tireless dedication to his in-depth research on unification, Nassim Harameyn's most recent scientific paper, the Schwarzschild proton, Schwarzschild being the solution, being effectively the outer limits of a black hole. So more or less it's event horizon. But the scientific paper, the Schwarzschild proton, received an award at the University of Liège in Belgium during their 9th international conference. Harameyn's paper won the prestigious Best Paper Award in the field of physics, quantum mechanics, relativity, field theory and gravitation. And he goes on to say, this significant paper marks a new paradigm in the world of quantum theory, as it describes the nuclei of an atom as a mini black hole, where protons, in other words, these mini black holes, are attracted to each other by gravitation rather than some mysterious, undefined, strong force. This radical new view of the quantum world produces a unification of the forces and appropriately predicts measured values for the nucleon of atoms. In his Crossing the Event Horizon presentations, Harameyn claims that the problem in current physics relates to the belief that gravity is a weak force, which goes back to the structure of the atom where all of the problems started. Oh, I do so agree with all of this. In studying the atom, physics were confused when they found a very dense positive nuclei in the centre of the atom, which defied their theory of mass, and then they found the negative electrons surrounding the atom that had a constant spin without losing energy and showed no signs of entropy. This created the first problem, and instead of resolving it through Newtonian physics, they created quantum physics with new forces and particles. Oh yes, I so agree. He goes on, under Newtonian physics, if you put positive particles together, they repel each other. However, in the nuclei of the atom, it has a dense structure of a black hole in a vacuum, but physicists did not consider gravity as the natural force to hold this dense mass together. Why? Let's have a quick look at that. Take that out, bring that in. Gravitational force. Gravitational constants G equals 6.67 M1 and M2. So if you've got two protons coming together, their two masses combined multiplied by the gravitational force divided by the distance between the two of them squared. As been known for a long time, it has been modified by relativity, of course, by Einstein's theories of relativity, but by general relativity in effect, but on a tiny level that we would be talking about with protons, then effectively that's how it would be. At the same time, the electrostatic force is another force at a distance, and the charge of the two, if we come down to the bottom here, electrostatic force is the charge of the two. So these two are both positive, positively charged protons, multiplied by k divided again by r squared, the difference between them. Now k is this awfully big number. This is an awfully tiny number. This is an awfully big number. And the reason for that is that k is actually, let me write it in here. Right. Excuse me if I stumble, but k equals 1 over 4 pi E naught, where E naught is the permittivity of a vacuum and E naught is 8.854 times 10 to the minus 12. Now if you have this small number on the bottom, that makes k this very big number. Okay, so if you try and force these two things together, these two protons together, what you're going to find is let me take all these dirty marks out. What you're going to find is the electrostatic force is far, far greater than the gravitational force. But you're going to force them together. What does that actually mean? Let me see if I can tell you what it means. Sorry about that. If we force these two together, there is no sorry, I'm getting a bit incoherent. Let me G and K both depend upon the distance, a distance. Now, if we go into the nucleus of an atom, once you get inside, what is the smallest distance that can exist? The Planck distance? Once you get inside that, then there is no distance. In effect, when you force these two together, the constants are unified to 1. Now, if we unify G to 1 and K to 1, then we wouldn't unify K to 1 because K would still be 1 over 4 pi. So, and we can disregard r squared because it'd be the same for both. But now we have a very different situation. Now we have F increasing, Fg, the gravitational force, increasing as this increases. But this now has become tiny. This is weak. This is massively strong compared to it. So once we have forced the two together, in other words, fused them together, then we have a different situation where the strong force that's holding two protons together is not mysterious at all. It's gravity, and that's what Nassim Haramein is saying. It is gravity. Let me just out of interest, gravity. Just supposing we had a planet, and somehow or the other, this is an astronaut. Now he's looking away from the planet. He doesn't know. How does he know that this planet has no atmosphere at all? He is not aware of the planet. He doesn't know it's there. He can't feel it. He's looking out here into the distant stars. To him, nothing's changing. Now, what's happening here? If we have, let's go back to the Leaning Tower of Pisa and drop a couple of weights from it. Now, if you've got no atmosphere, they will both land at the same point. They've done these experiments on the moon. You know, drop the feather and the hammer, and they both fall at the same rate. But do they? They are falling at the same rate. They'll hit the surface at the same rate. But what's much more? There's our hammer, and there's our feather. There's the surface of the planet. Hammer, feather. It's much more accurate to say that the surface of the planet is coming out to meet these two. These two aren't going anywhere. This is what happens if you study relativity. You will see these kind of things happening. Of the force we feel as gravity is effectively the mass of the planet behind us taking up the space. This is not my idea. This space in between is being taken up. So this astronaut has no idea that this planet is taking up the space between him and it. Effectively, it is growing behind him. It is, in a sense, growing, but it's eating up this space. So he won't be aware of that planet. He's still looking out here. Nothing seems to have changed out here, but right behind him, this planet has changed, and he'll know about it when he reaches the surface, because it will collect him, and according to the density of it and the size of it, if it happens to be massive or very, very, very dense, it's going to hit him hard. So if this was an Earth-sized planet with no atmosphere, by the time he reached the surface, well, there'd be too much left of him. So what we have is not things falling, but the mass itself taking up the space. Let me just... Oh, no, I didn't want to do that. Excuse me. So I just wanted to add a layer. Where am I? Layers. Sorry, here. There's another layer. I beg your pardon. So. This one. Get rid of this one. Sorry about that. There I am. Another layer. So, let's say the Earth is the moon. The moon is in free fall. It's going in a straight line. All that's happening is, as it's moved out to here, the Earth has effectively eaten up the space between it. There it is. Same thing happens. It moves out to here. The Earth has eaten up the space. So from the outside, from the moon's perspective, it's going in a straight line. From our perspective, the moon is caught in this orbit. And that's how mass curves the space. And a black hole then is so dense that it curves the space so much nothing can get away. Now, let me just go back to here. Now, if I have a black hole, if we had a whole universe, the whole universe had one black hole in it, let's say it was one black hole, could it exist? I mean, it have an event horizon and it has all this gravity, but what does it mean? It doesn't mean anything. There's not, all you have is this energy point in space and then nothing. It has no event horizon. There's no event. There's no time. There's nothing to gauge it by. It doesn't exist. It doesn't exist until we have another black hole. Let's say this is a proton. Can a single proton exist on its own? No. It exists with respect to another proton. And this proton has its event horizon. This proton has its event horizon. And they're both trying to eat up this space. This space in between. They're both trying to expand into this space, but they can't. They're actually pushing each other away as they eat up the space. which is what the electrostatic force is. That's where your electricity comes from. When you have two protons sitting there nice and peaceably, but then you expand this one suddenly, it starts to cause this friction with those around it. And so we see that as electromotive force, as electricity, static electricity, whatever type of electricity. So here we have the two protons. Now, the fact that one cannot exist on its own in a universe on its own gives you this, why I call it absolute relativity. Because without the relativity, without the positioning against other protons, then it's meaningless. It doesn't exist. The energy only exists. The energy of a proton only exists from a datum point of somewhere else, and that somewhere else, if it's not a proton, it's not anything. Therefore, it's not. So it's an absolute relativity. So we have no electrons doing this. The electron that supposedly moves when you create electricity, the electron passing on is the energy of the extra energy of the over-energized proton that's sitting there quite peacefully with all these other protons, but then gets energized by whatever force, and it's got to get rid of this because you have this friction with the other protons in the system, and so we have our electromotive force. So there's no electron involved. It's protons only. There's no photons. I've gone on to explain why there are no electrons, no photons. There are no quarks. There is no... I did explain why there are no Higgs boson. You don't need that to give these protons mass. If you increase their energy, you increase the mass. That's it. It's as simple as that. And photons have no mass because they are an instantaneous effect of energizing protons. I've done all this in previous videos. I hope you've seen all that. So that's what we're looking at. That's what curved space is. So these two protons are both eating up this space, and because they're both eating up the same space here, they repel each other. So the gravitational force of a black hole creates the electrostatic force, and it's not until you drive these two together so that they are so close, effectively they start acting as one. So you have fused them, and what might happen is one of them become absorbed and become a neutron, a proton, a neutron. It doesn't actually happen like that because you're more likely to end up with two protons, two neutrons. So you've gone from a single proton, effectively a hydrogen atom, to fusing two protons, four protons, two of which are turned into neutrons, and there you have your helium, and so on. So that's where we are. That is what is at the heart of the proton. No quarks, none of that stuff, just black holes. Each one is a black hole, and everything is made up of these black holes at their different energy levels. Isn't it wonderful? And so, what I wanted to do then, look at what we've done. We've actually unified the gravitational force with the electrostatic force, with the strong force. Okay. The strong force, the electrostatic force, gravitational force, they're all the same. Well, what's left? The weak force. What is the weak force? This is total unification. This is what how do I mean is starting to indicate, but he still includes quarks, etc. And no, it's much simpler than that. So we've unified all those forces. The only thing we haven't looked at is the weak force. What is the weak force? The weak force is the force that... A strong force is the force that holds atoms together. And we've said now that that is gravity. Okay, and that gravity creates the electrostatic force, which tries to keep particles apart. But the weak force is that which enables atoms to decay, to fall apart. Which atoms fall apart? When they do, they're radioactive, right? They give off particles. So uranium will sit there and you put a Geiger counter on it. If you've got a big enough bit of uranium, I'm told you could feel the heat from it as it's decaying, and it's letting off alpha particles, which are in fact these. But the extra energy that goes with it when that decay happens is supposedly the weak force, and is the thing that is dangerous. You don't want your cells to take on that extra energy, because it will pull them apart. So, what is this weak force? Now, to do that, what I need to do is I've actually I need to revisit the construction of atoms. Now I hope I can do this on a drawing here. I'm actually kind of revisiting one of the previous videos which looked at how atoms are put together, and showing that electrons do not exist, that the diagram of, say, a helium atom has its two protons, two neutrons, two electrons, and I'm saying no, it's much more accurate to say that where the electrons have been shown, that's actually the protons themselves. So you got two neutrons and two protons. Yeah. So we'll start off with that. We have a single proton, but then when two protons are joined together, we get this. We're just talking about the protons at the moment. Okay. And this is shell N1. It's going to get really dirty, this, so bear with me. Then we can add another two. Do you remember I said that they add on this same line? If you haven't seen this, please refer to my previous videos. But these are all the S shell. And now, on here, we have the P shell. SPD. This is, so effectively, these are what constitutes N2, but it's split up into the S, which is running around here, and the P. S, P. Now, what I can do is just diagrammatically where there's a gap in the energy here, then we have the other protons circulating in that gap. I say circulating, you know, they are orbitals in this gap. So there we have the S and the P. Now if you count that up, the first S on the N1, these two constitute N2. First on N1 had 1, 2. One on N2 had these two on the S orbital, and 1, 2, 3, 4, 5, 6 on the P orbital. And so let's go again. The next one out, we add another, and as we add these, you get the different element. This is S again, and now we have this P going around here, and another, and we're further out, we're gaining energy all the time, and so we have sorry, this should have come from here, like this. We have these three. Told you it was going to get dirty. Now these come out to here. And these are all N3, and there's the S, there's the P, and there's the, what do we have? D. And take up the gaps again, there, there, and there. New one there, and there. So that's the pattern. As we go out, it keeps to this pattern where we have these S shells and then the P, the D, etc. Subshells with their extra ones. So each time you'll replicate what went before and then have a new outer circle with a new outer energy with a new vacancy where you've added here and here, where you then add another 4. So each time you add, you then add another, you can add another 4. Now the thing is, another 4 protons. Now this is the pattern of the protons as the thing grows. Now the thing is that that's all very nice and neat, each subshell coming outside of the one before. But as you get further out, the subshells kind of lap over because you're then getting so close together, the next subshell ends up inside one of the other subshells. So you can study all this, you can see it's not as simple as it starts off, because these subshells these shells are getting closer and closer together. So each time, I haven't drawn it like that, so it would go like this, and then they would be smaller, and then they will be smaller, and then it will be smaller. And so because they get so tiny, the difference between them starts to blur. But the thing is, what we have are these systems. Now, each of these systems then can take, say, let's say, supposing this atom here and this atom here are at exactly the same energy level with the same spin. These two will be at the same energy level with a reverse spin. These two can have 2 neutrons attached. So you can start to get more and more neutrons. A neutron can be in this system with these two, in the system, neutrons in the system with these two in the system. So where they're paired, you can get a couple of neutrons, but this atom and this atom can be paired, so you can end up with more neutrons. You can pile in more neutrons, in other words, which is what happens when you start getting up to uranium level. You end up with, let me just delete that, uranium, you end up with 146 protons and 92, what am I saying? Cross that out. Neutrons and 92 protons. Now this thing, now you've gone way beyond, you've got all these shells, you've got these systems with their neutrons. You've got these systems hanging out on the edges of these, where everything's blurred, where you've hardly, what you're getting here is these ones on the outside now are losing gravitational consistency with the inner ones, because they're so far away, they're so far away in energy that then this tug of war between the gravitational and the electrostatic forces is starting to change. And what we'll get is, this is so energetic of its own system that it peels away from this now cumbersome atom, the uranium atom. It peels away, and it will peel away in the form of two protons, two neutrons. So it will give off an alpha particle. And in doing so, it releases this energy, which is deemed as the weak force. So that's all that's happening there. And it's all to do with the gravitational force that is at the heart of every proton. The gravitational force that is at the heart of every atom. Atom that has been constructed during natural processes. The natural processes that force them together in the decay of stars and so on, or first of all in suns, and then the decay of in stars, and then the decay of stars and the stars exploding and everything, and then stars explosion will make the much heavier elements. You need you need huge power to create uranium. But then it sits there, and it's so cumbersome. It sits there and it cannot hold. It starts to lose some of that energy, and the outermost particles then peel off or are thrown off by the increased electrostatic force on the outside, where it's suddenly won in the tug of war against the gravity. The particles on the outside are holding together because they are together with their protons, but that whole system is not held tightly enough to the inner core, and then it's able to, it's forced to be ejected, and this ejection is radioactivity. It's the decay of the atom, and in the case of uranium it will decay until it's decayed into lead. And at that time, if you would look at the lead atom, everything is nice and neat and it's stable. There it is. And there were talk of protons eventually decaying. Well, I don't think that could ever happen. A proton will not decay. It's got nothing to decay into. It just is this black hole in space. That's what it is. So, no. I've gone and put on this thing what they are not. I meant to edit that out, and that should say what they are. I'm going to have to leave that. That's another cock up. This is An Absolute Relativity, video 9, protons, what they are. You've seen what they are. Let me take that back out again. What they are is not electrons in the orbitals, but protons in the orbitals. That's what protons are. They are black holes. Okay, I'm going to produce a brief summary video of all this, but I hope you've been able to follow this through. We've said that at the heart of every atom the heart of all atoms are made of protons. Protons and neutrons are protons. They're all protons. The protons are tiny black holes. And it's the gravity of the black hole that is the strong force that enables two protons to fuse together and not be forced apart by electrostatic force. And the electrostatic force is just the two protons trying to eat up the same space. You force them together, well, you need a lot of energy to do that, but that's what fusion is. You force them together. In forcing them together, they will work as one, and so on. So there we have gravity, electrostatic force, the strong force, and then the weak force is where the atom keeps fusing together more and more and more, but it becomes on its outer limits much more unstable, and then that enables the electrostatic force to come back into play and force the essentially stable alpha particle out of the unstable cumbersome atom. So strong force, weak force, electrostatic force, gravity, they are all the same thing. That's unification. That's it. We've unified the four forces of nature. That's everything. So again, I will make a very short summary, but that's it. You can see why it was called An Absolute Relativity. There is, everything is, the existence of atoms is absolutely relative to the existence of other atoms. The existence of protons is absolutely relative to the existence of other protons, and that's it. Everything comes from there. So, thanks for being here in this one. I hope, if you haven't been through the whole series, I hope you choose to, but I'll see you in the next one where we'll do a little summary. See you then. Bye bye.